So how do we find the volume of solids? Now the volumes we're looking at are things that have circular cross sections. So we can create the solid by rotating a function about a line, and that line, for convenience, could be either the x-axis or the y-axis. So I'm going to do it around the x-axis. So we're going to rotate this shape around there. So the way we think of it is that we're going to chop up this area into rectangles, much like we did with the integration, to find the area. We're doing the same idea. But then we're going to rotate that slice. So every one of these slices we're going to rotate. And we end up with, well, it's a very small cylinder. Some people call them discs. And we could easily find the volume of that. The radius would be whatever the y value is at that point, and that would be equal to function x. And so the area of the circle, so the cross-sectional face, would be pi times the radius squared. So pi times function x squared. Then what we'd say is, well, okay, so each of these volumes, and the volume's going to change because all the slices of different sizes, but that would be the area times the height, and the height would be whatever the change in x value is. And so we ended up with this, limit as delta x approaches 0, and then we're going to sum, or we're going to add all of those slices together. Well, effectively, that's still just integration. If I factorise the pi out, all I'm saying is I'm summing up all of these things, all of these areas. Function x squared is just the area of the cross-sectional face. And that's how we created integration in the first place. So it's still just the integral. So the volume is just going to simply be pi times the integral from a to b of whatever the function value is, squared dx. So here's a random curve, and I'm going to go from a to b, rotate the whole shape round, and we get, what would it be? One of those things you stick flowers in, I suppose. Or vase or vase, depends how you say it. That's why I just said one of those things you stick flowers in. So the volume of that solid that's created by revolution, so we call them volumes of solids of revolution. Easier way to remember it is rather than saying function x, you just say the y value. So we get pi times the y squared dx. That means we have to substitute the function in for y because everything's in terms of x. That means our limits also have to be in terms of x, so we're going from a to b. If we're going around the y-axis, then the formula would become x squared to y. If we go around the y-axis now, everything's in terms of y. So the limits would be in terms of y, and x squared, well, we'd have to substitute in whatever x squared is in terms of y. How do we remember it? Very simple. If we're going around the x-axis, then we know we need it in terms of x. If we're going around the y-axis, then we need it in terms of y. So let's now go and prove some of these formulas that you've always just taken for granted. Your teacher said to you, well, this is the formula for the volume of a cone, and you just accepted and went, oh, good, yes, look, that works, that's fantastic. Well, let's prove that it works. If I want to create a cone, I can get that shape by rotating this line around the x-axis. I'll go from 0, and conveniently I'll call the x value h, because that'll represent the height of the cone once we rotate it. So we're going to rotate it. Whoop, there it is. So we have our cone. There's a shape to give it a little bit more, well, obvious what we've got there, just in case my little sketch doesn't quite bring it out to you. So there's one of those wire diagrams of it. So I'm going around the x-axis. So I need y in terms of x. Well, I know that. Y is mx. So if I square it, I get m squared x squared dx. Well, m squared is just a constant. I can factorise that. Integrate x squared, add 1 to the power over the power. Sub in h, sub in 0, and you can see we get the formula for the volume of a cone. I'm sure you recognise it. 1/3 pi m squared h cubed. Anyway, hang on a sec. That's not what normally we see. And that's because my formula is in terms of the slope of the cone. Well, that's not what we normally use. So let's get to what we normally use. R would be the y value, because it's the radius of the base. And slope, we know, is rise over run, so it'll be r over h. If I sub that in for m, you can see, there we go. Now it looks a bit more familiar. 1/3 pi r squared h, it comes out to be. Let's try the sphere. So if I want to rotate, now interestingly, we don't actually rotate the whole circle. We only rotate the semicircle, because we're rotating 360 degrees. If I rotate the whole circle 360 degrees, I'm going to get twice what I need. because both the bottom half and the top half would go round and sort of get twice the value. So it's actually just the semicircle that I'm rotating there. And there we go. It was a bit harder to get that Y diagram. It doesn't look like a sphere. Trust me, that's a sphere. It's just the orientation. I ended up moving it too so you can see the sort of shape. Pi times the integral of y squared dx. Well, I make y squared the subject here. We get r squared minus x squared. Remember, I'm only going from 0 to r. That's why I've gone 2 pi. I'm taking advantage of the symmetry of the shape. Integrate that, r squared x minus a third x cubed. Sub in r, sub in 0, and there's our formula, 4/3 pi r cubed. Find the volume of a solid when the parabola y equals x squared is revolved around the y-axis this time, and I'm going to go from 0 to 1. There's my standard parabola. We're going from 0 to 1. Again, I only rotate half of the shape. I don't rotate both halves. I mean, you still end up using the y equals x squared because you're going to square the function anyway. So half of it would like be what would it be? X equals the square root of y, wouldn't it? But when you square it, you come back to y equals x squared. So rotate that around the y-axis and we get the shape known as... Oh, hang on, whoa, I heard it. Thank you. It's a paraboloid. And there's my wire drawing of it. So this time I'm going around the y-axis. So x squared to y, x squared is in fact y to y, because we're going around the y-axis. Integrate that, we get a half y squared, sub in 1, sub in 0, and it's pi on 2 units cubed for that one. Find the volume of this solid. The shaded region there, so the triangle, is rotated about the x-axis. So what are we going to get? There's a bit, can you see it there? You basically we've got a cylinder with a cone cut out of it, or drilled out of it. So that's what the wire diagram there is trying to show. So all right, you've got to look at your boundaries. So I'm going around the x-axis. So each of those slices that we would have looked at, the top boundary is the line y equals 5. The bottom boundary is the line y equals 5x. So similar to what we did with area. Top boundary minus the bottom boundary. But you square them before you subtract them. Because you're saying it's the volume of the top boundary minus the volume of the bottom boundary. So it's 5 squared minus 5x squared. So we get 25 minus 25x squared. And that tidies up to be eventually 50 pi on 3 units cubed. However, there is an easier way. Just the same as I said with area, if we got a formula for it, use the formula. Remember I just said, it's the cylinder minus the cone. You drew the cone out of it. The cylinder is pi r squared h. The cone is 1/3 pi r squared h. So I'm left with 2/3 pi r squared h. We obviously come up with the same answer. So take advantage of, if it's a basic shape and you've got a formula for it, take advantage of that. I was trying to get that wire diagram to illustrate it, but your eyes are playing tricks with you. Some of you are seeing a cone which is like got a bump inside it. Some of you are seeing that. But actually that's not what's there. You've got to look at it closely. Imagine it the other way around. You've actually got can you see it? It's popped the other way. Yeah. So it was really hard to draw a wire diagram for that one.
Which way do you see the cube?
Yeah. Here's an HSC one. And it was in a 2-unit paper admittedly, but as I say, it's no longer in 2-unit. It's now 3-unit. So we've been given 2 parabolas. I'm going to need the point of intersection. They actually told me to find it. Solve them simultaneously. And we get x is plus or minus 2. But they did ask for the points. I just put a point down.
Whoa.
Yeah, I know. I wonder if I would have got marked wrong. Because I just looked at the shaded area and went, oh, well, that's the bit I'm interested in. But technically, the question did say points. But I did say x is plus or minus 2. Anyway, the shaded region. Okay, so that shaded region is rotated around the y-axis, They'll give us a hint by splitting the shaded region into 2 parts. Why 2 parts? Again, just like area. If the boundaries change, then we need a separate integral for it. So we go into the y-axis. If I start up here at the 12, I've got the upside down parabola going to the axis. But after we get past the point of intersection, It's the concave up parabola to there. So I'm going to have to do it with two integrals. So there's our shape. There's the wire basket of it. Yeah, cool. It's an Easter egg. Maybe a bit sharp at the sides for an Easter egg, but you can think of it like an Easter egg. We're going around the y-axis. So x squared to y. We're going to split it there. So I need to make x squared the subject here. So x squared is y. That one was easy. The other one becomes x squared is 6 minus a half y. So I have the two integrals, one going from, have I got it the right way around? 0 to 4, yep, good. So 0 to 4 on the y to y. Second integral, 4 to 12, sub in. There we go. We end up with 24 pi units squared. 11G.